Okay, so I'm Meghan Dalton, and I work with the Climate Impacts Research Consortium. And so I'll talk a little bit about what CIRC is doing on the research side to support SBU's climate impacts assessment, and highlighting some of the researcher utility manager interactions as we go along with this project. So CIRC's tasks in this project is one to downscale the global climate models and tailor them for use by SPU's models. And I'll go into some detail about that later. Secondly, to evaluate the GCMs and the custom downscaled data, testing, how good is this data? Is this data good? And also, which models are producing observed climate better than others? And I'll talk about that a little bit too. And thirdly, to investigate future changes in relevant questions, such as the timing of fall rains, forest fire danger, and the frequency of exceeding operational thresholds. And then fourthly, to dig into the literature and understand what's the current understanding on changes and future changes in atmospheric rivers and El Niños and Pacific Decadal Oscillation. So for this talk, I'm going to focus on these top three, and I'll just show some preliminary results from our analysis on the return of fall rains. So firstly, for downscaling the GCMs, we start with 20 global climate models from the Coupled Model Intercomparison Project Phase 5, the most recent set of climate models. And these models are at a resolution of 100 to 200 kilometers, which are essentially can't be used by SBU to do their impacts assessment, because they need data on a smaller scale, both spatially and a smaller time scale too. So we've statistically downscaled these 20 GCMs using the multivariate adaptive constructive analogs method, MACA, that John Botzklou and Catherine Hedgewich at University of Idaho have produced. And then we've taken that one step further, because what the MACA downscaling provides is 6-kilometer gridded data. But SBU's hydrology model uses weather station data as inputs, and so we needed to do one extra bias correction to make sure that that data was matching up with the observed records that they use. And then the fourth step that Joan mentioned is that we needed to convert this daily data to hourly, because their model uses hourly data to derive the hydrologies. So to put this in pictures, this is what a typical GCM resolution looks like, 100 to 200 kilometers. And in that center, to orient you, this is Western Washington, if you can see the black state outline up there in the Puget Sound in the top left corner. In the middle grid box, these are black dots that show the locations of the weather stations that drive SPU's hydrology model. And you can see they're all in one grid box. So what the GCM knows is that downtown Seattle and Snoqualmie Pass experience the same climate, which we know that's not right. So what MACA does is downscale this data to 6 kilometers to provide some more spatial detail in the downscaling, and this preserves the gradient of climate between downtown Seattle and the mountains. So you can see on this plot here, the station locations are indicated as well. And so the next step that we do is we extract the time series from an individual 6-kilometer by 6-kilometer grid box, and we bias correct that to the statistics of the station data at that same location. And this bias correction is the same type of bias correction done in the downscaling for the MACA. So it's very consistent methodology. And so what this does is it makes the station data from whatever the period of record was, it makes the downscaled MACA data match the statistics. So it'll have the same mean and the same standard deviation, all the quantiles will match up with the station observations. Sorry, that doesn't mean that the day-to-day sequencing will be exactly like the station observations, because the downscaling does not, cannot fix that because that's something inherent in the climate models that they simulate the daily sequencing differently. So then the final step is to bring this daily data onto the hourly time step. And what we've learned is that how we do this matters quite a lot. So the function that SPU's hydrology model uses by default when they don't have hourly data available is that they use the daily data and disaggregate it to hourly by spreading the daily precipitation evenly over a 5-hour period between 4 a.m. to 8 a.m., a particularly cold time of the day. And what they found out with some preliminary analysis is that this was making the hydrology timing and magnitude pretty off. This is the discrepancy issue that John alluded to. So in the winter, all the squiggly lines together, those are different models, and the blue line there is what we'd want to try to match it to. So what happened is that in the winter time, there was too little stream flow, and in the spring and into the summer, there was too much stream flow. So what ended up being the problem is that because we were making the precipitation fall during a really cold time of the day, that was biasing that precipitation to fall more as snow than as rain. And so there ended up being too much snow accumulating in the winter time, which reduced that wintertime stream flow. And then when it warmed up to melt, there was a lot more snow that was then coming down the river and causing too much spring and summer flow there. So this prompted CERC to look into the sensitivity of snow to which 5-hour period this daily data was aggregated to the hourly. And this is an analysis that Catherine Hedgewich at University of Idaho did. She looked at, she took hourly data from a SNOWTEL station, and she used an empirical snow model to compute the amount of snow. And then she took that hourly data, aggregated it up to daily, and then disaggregated it back down to hourly using this 4 a.m. to 8 a.m. Time period. And she also varied the start of that 5-hour time period, starting at each of the hours during the day, and then computed snow for that. And so what she found is that 4 a.m. to 8 a.m. period to disaggregate the daily data to resulted in about a 40% bias in snow, so way too much snow. And then the smallest errors can be found right here from if we disaggregate the daily data to hourly at 7 a.m. to 11 a.m. Or conversely 9 p.m. to 1 a.m. So we took this study and we applied this then to SPU's hydrology model. And what we got, this is a plot showing how well the different disaggregated data resulted in these hydrologies. So we're trying to match the black dashed line. And so we have starting the hourly disaggregation from 6 a.m. all the way through 10 a.m. And you'll notice that the later we get into the day, that hydrograph kind of shifts and matches up a little bit better. And it converges on about 7 a.m. perhaps being one of the better time windows to match up with that observed hydrology. So this is an example of a problem and solution we maybe didn't expect when we started out, but it required some joint understanding and isolating the problem. It's not something that CERC could figure out in isolation without SPU's understanding of the hydrology model. And it also took CERC's understanding of snow dynamics to really come together and figure out the solution. And so like Joan mentioned, we first thought, okay, let's figure out, make sure the downscaling was right, the hydrology modeling was right, everything was fine, and we really isolated this hourly disaggregation issue. And together we have a meeting tomorrow, and we'll talk through and select the path forward for which hourly window we'll use going forward. So switching gears, I want to talk briefly about GCM evaluation we did. In general, it's best to use as many GCMs as you can when in impact studies, at least 10. And you want to make sure that they simulate desired aspects of climate well, but that you also choose models that span a range of future outcomes. Not for this project directly, but David Rupp and others at CERC evaluated the GCMs over the Pacific Northwest, and that information we boiled down for SPU to understand which GCMs are performing better for the Pacific Northwest. And we also evaluated the downscale data at the station level that they use to ensure that the biases that are supposed to be corrected with downscaling were indeed corrected, and also highlighting some models that match the daily sequencing better than others. So what we found essentially, these are, on the left are different metrics that we looked at, such as the variability of temperature and precipitation trends. This is consecutive dry days, consecutive wet days, or the maximum 5-day precipitation, maximum 1-day precipitation, and a cold spell and warm spell duration index. So these are all daily sequencing and serial correlation metrics that won't necessarily be bias corrected when the GCMs are downscaled. But what we found is that some of the same models that performed well in David Rupp's study also performed well looking at these metrics. So there's a lot of consistency here, which is nice. So now I'll move into some preliminary results of an analysis that we did on the return of fall rains. So SPU defined a metric for what is the return of fall rains. And they said that it was when a 7-day cumulative sum of 2.5 inches or more precipitation was reached at this Landsberg Co-op station at Masonry Dam. And I modified that to start counting at August 1st, which is the lowest precipitation time of the year. So doing this for the station observations, which is in black, and for the downscaled historic in blue, and the downscaled future in red, I've plotted the percent of years that reach that threshold on a given day. So if we look at October 1st, if we go up and we look at the blue line, we see that about 40% of years reach that return of fall range threshold by October 1st. But into the future, and this is at the end of the 21st century, the percent of years reaching that threshold by October 1st decreases. So essentially, the likelihood of the fall rains returning on a given day shifts later by about a week, just under a week. So that's what we found there. And we briefly looked into the synoptic situation here, looking at the geopotential height anomalies versus the day that the fall rain returned according to the metric. And there is a positive association here with later fall rain return corresponding to higher geopotential height anomalies and earlier returns with a lower geopotential height anomaly, which is to be expected. So I wanted to close with a few things that we're learning through this project, this engagement. Joan mentioned a white paper that WUCA is producing to gather all the lessons learned from all the PUMA projects across the country. So I think the interesting things that we're learning that are perhaps different from what other utility researcher partnerships in the country are learning is that SPU is asking these operationally relevant questions, like the fall rains or the fires or precipitation thresholds that are going to be woven into these climate stories to help better communicate that to the public. And we're also learning the importance of really testing the data and digging in both on the climate side and on the hydrology side to make sure that what we're getting is something good. And we're also learning all the different aspects that we need to work out to make this process go smoothly. This is a new venture for SPU to create these hydrologies in-house, and so making that transition is, and having the researchers not doing the modeling themselves. It takes a lot of cooperation and fine-tuning to make that process go smoothly. And as Paul Fleming would elaborate, it's often desired that there could be one big repository of this downscaled data that can be applied to everyone, all utilities. But what I think we're finding is that one size fits all may not fit for everyone, and that some level of customization is needed. Depending on the context that we're doing these impact studies. So with that, I'll close, and Joan and I can take some questions.
I had a question about the customizing that you had to do for this area. So the MACA data, and maybe I'm not understanding, but that's available for anybody to use without the customizing. And the USGS has this web-based thing where anybody can pull up a watershed and get scenario or get projections from that. What is there a message we should learn from this in terms of using these off-the-shelf products if some naive person like myself was just to go to the USGS site and pull up my watershed I'm interested in, that you ought to know about all the modifications you had to do to the off-the-shelf downscaling?
I don't know exactly what the data available on the USGS site is, but the MACA data at the 6 kilometer gridded resolution is available online. Anyone can go and download it. For using that downscaled data in impact studies, I would say that we're learning that you do need to really test it and make sure that what you're getting makes sense. And it's sort of along the lines of understanding your system well before you can understand what changes in the future are going to be. And I think this is part of understanding the system, how the historically downscaled data matches with the observed data in your area of interest.
Hi, this talk focused on the Cedar. I was wondering if the same kind of work is happening on the Tolt River as well, since I know there's a dam up there too.
So there's a few stations on the Tolt that we are looking at too. I think we're focusing on the Cedar River since that's a major one. But yeah, the Tolt is being considered in this project too.
I had a question about how you might explain that you're seeing this delay in return of fall rains by a week, but a lot of the GCMs project an increase in fall rains. So, but maybe there's a shorter duration of what we consider fall. So how might you explain that?
Yeah, I would probably explain that with the definition of what fall is. So we're in the Northwest, projections for precipitation are an increase in seasonality, decreases in summer, and increases in other seasons when it's already wetter and summer's already drier, so we'll decrease more. But where that line is drawn from where we start seeing decreases or increases, I think that's where this analysis on fall rains kind of focuses on. So I think that's a definition of what you call fall for the models. But that seasonality is increasing, and this analysis on fall rains is consistent with that aspect of the GCM projections. Great, thank you.
I have a question for Joan. With using the ensemble approach with the GCMs, it seems like you're kind of bracketing the uncertainty in the projections. I'm wondering from the standpoint of the hydrologic or utility models that you're using in-house, what the confidence level that you have is in that, and how you're kind of addressing the uncertainties in those two steps of this process.
Well, the plan is to run all 40 models through the complete chain. So we haven't really looked at the uncertainty and the variations in that. What you did see with that preliminary analysis is that the hydrology between the different GCMs didn't look that much different, but then it does what controls the water system are the extreme events, the low dry, the real dry periods. And so little differences between models during that time period can really change the water supply outlook. And we will definitely be looking at the full range of scenarios and be looking at the uncertainty. What does that tell us? Because we do expect to have differences in the results.